the day. So my name is Manabendranath Bera. So before we go to the first talk, let me introduce the speaker we have for the first talk of the day. And the speaker is Dr. Min Jiang. Dr. Min Jiang received his BS degree in 2013 and PhD degree in 2019 in the University of Science and Technology of China. Now he is a postdoctoral fellow in the same university. His interests mainly focus on quantum precision measurements and nuclear magnetic resonance, including ultra-high sensitive atomic magnetometer, ultra-low field nuclear magnetic resonance, and tests of fundamental physics. His works are ongoing towards developing sensitive techniques for applied science and searches for new physics beyond standard model. So today he will be talking on zero to ultra low field nuclear magnetic resonance and its application. So over to you, Dr. Min Jiang.
Yeah,
Please start.
thank you for introducing. Yeah, I try to. Okay. Is my slide visible now?
Yes, but not yes. Now it's fine. Yeah.
Yeah, it's okay now.
Yes.
Okay. Thank you very much. Yeah. Hello everyone. Yeah, my name is Min Jiang from USTC. At first, I would like to thank the organizer for inviting me. It is my great honor to present our some recent work, zero to ultra low field NMR and its applications. So in the following, I will introduce my talk from three parts. In the first part, I will try to explain why we need zero and ultra low field NMR. And second, I will introduce how we realize the ultra low field NMR based on atomic magnetometers. In the third part, I will explain what kind of applications
Dr. Jiang, we cannot hear your voice.
Yes, you are audible.
Maybe he can switch off his video to stop to save bandwidth.
Yeah. Dr. Jiang, if you can hear us, can you please switch off your video? Okay, I write him on the chat box. I wrote him.
It seems like he's speaking, but sound is not reaching us.
Yeah.
Hello.
Yes. Yes. Dr. Jiang. Yeah. Can you hear us? We cannot hear you. Yeah. So maybe you don't switch on your video, only share your slides. Yeah. Sorry, we are having little bit of technical difficulties. We will get back very soon. So, Dr. Jiang, can you still hear us? It could be that you switch off your video to save some bandwidth. Yeah, but we cannot hear you. We cannot hear you. Seems he's, yeah. Yeah, maybe you switch off your video and share the screen. That might work. Mhm. No, we cannot hear you. Neither we could see your video, but you may switch it off for the time being. And it seems that you're trying to share the content, but it's not loading. Okay, can you hear us? We cannot hear you yet. Ah, um, Sandeep, our speaker requests us
Hello. Yeah.
and go for the, yeah, can you see? So,
So next speaker is
Aditi, Aditi,
Professor
D.
Aditi. So if she's ready, we can move on to that.
Huh. Aditi, you're there?
Yes, I am here. I
Uh,
start.
is it possible for you to,
Yeah,
yeah?
just
Okay,
yes.
okay, okay. No worries, Dr. Jiang. We understand the problem. So now we switch to the second talk of the session at this moment. And if there's some time left, we will come back to the previous talk uh, if the technical problems are resolved. Okay, so let me introduce Professor Aditi Shende, who will be speaking next, quickly. So Dr. Aditi Shende is currently a professor H at Harishchandra Research Institute, HRI, Allahabad. Along with Professor Ujjal Sen and Arun Kumar Pati, she has started the Quantum Information and Computation Group, QIC Group, at HRI in 2009. Currently, the group consists of 3 faculty members, Arun Pati, Ujjal Sen, and herself, 15 PhD students, and 5 postdoctoral fellows. She did her doctoral work in the University of Gdansk under Professor Marek Zukowski, and subsequently was an Alexander von Humboldt postdoctoral fellow with Professor Levenstein, Maciek Levenstein, in Hanover, a Ramani Cajal Fellow in ICF4, the Institute of Photonic Sciences, Barcelona, and an assistant professor uh, in the Jawaharlal Nehru University, Delhi. Today she will be talking on quantum networks. So with this, I will request Professor Aditi Shende to start the talk. Over to you, Aditi.
Yeah,
Thank you.
thank you. Thank you very much, Manav, for the introduction. And also thank you, organizer Kobita Sandeep, to arrange this conference in this critical time. So it is true that we are not able to contact everyone during this pandemic, but at least in this meeting, we can see our entire community and feel good. So this is really nice that you took this pain. So can you, so I shared the screen.
Yes, yes, it should be enabled, no? Ah, yes, it's
Yeah,
coming.
so can you see the screen?
Yes, yes,
Yeah, it's full screen now, right?
yes, yes.
Okay,
Yes.
okay. Maybe I off my video. So can I do that without?
You just have to click on the video, the start video.
I think stop video. Now
Stop
it's,
it, yeah.
Okay.
Yeah.
Okay, so I will be talking about quantum network. I will tell you what do I mean by quantum network, and the work is actually based on 2 papers, 2 of our recent papers. One in physical review research in print, another is already in physical review A. So the main pilots of this work, they are Ratul, Srijan, Amit, and Shiladitya. Ratul and Srijan is my PhD student. Amit is in IIT Palakkad faculty now. Shiladitya was a postdoc at HRI, now moved to abroad. So actually recently moved to abroad. So the outline that I'm going to follow is as follows. So first I will tell you sharing entanglement, what are the procedures known to share entanglement over large distance. And then I will briefly describe the way we can identify entanglement after sharing. This is for this community, the tools that I am going to use are known, but for completeness, I will tell this. Then I will tell that in this way, actually, one can address some fundamental questions like superadditivity in non-classicality or non-locality, which is also known as activation of non-locality or superactivation and so on. Then I will talk about quantum network in different lattices, like one-dimensional and two-dimensional lattices. I will show that in this, in our proposal, in this network, one can share entanglement, and at the same time, it is possible to certify entanglement. And finally, I will conclude. So let's start with sharing entanglement over large distance. So network means it is a collection of nodes and connected by edges. So these are the edges and they are nodes. And our dream is to build such a network, but that network should contain entangled states, or these edges are entangled. Now, why we require to build such a entangled quantum network? Because we want to share information among arbitrary number of parties situated in different locations. Here I should mention that these different locations can be different cities, different continents, just like also in a quantum computer hardware where we want to actually want to transfer information from one node to another one. So these quantum network building can be an important part both in the communication theory as well as in computation. Now, information can in general be classical or quantum. Now, in both the scenarios, we know these entangled states can enhance performance of sharing classical or quantum information among arbitrary number of parties. So we can tell that in this network or in sharing information, entangled states are resources. There are a lot of challenges when we want to share entanglement in quantum network. And the challenges are due to decoherence. So either the system cannot be prepared as isolated. So system always decohere after interacting with noisy environment, or the informations can be sent through a noisy channel, which also decreases the performance. There can be an experiment detector inefficiencies and so on. However, over the years, especially in last few years, we saw great experimental achievements. And that actually motivated us to propose or to work on this quantum network, because it's already, it is now possible to do this experiment in laboratories. So probably the first achievements that I think everybody has talked about is this satellite-based entanglement distribution over 1,200 kilometers. And as you know, they use the polarization degrees of freedom of photons. There are also, it was reported that multipartite or multi-site entanglement is also possible to create. And even in photons, there are recent article where it shows that 18 qubit entangled states are prepared. Here, of course, they have created 18 qubit Brinberger-Horn-Zeilinger entangled states by using 3 different degrees of freedom: path, polarization, and orbital angular momentum. You have already heard talks based on entangled states. Heard talks on preparation of entangled state based on orbital angular momentum in this conference. Now, there are also other physical systems in which multi-site entanglement can be created. For example, this is the experiment in ion trap, where you see that the 20 qubit entangled states has been created by using calcium ion. And they're able to prove that this 20 qubit state is multipartite entangled for a certain time. Also, in a recent time, it was shown that by using superconducting qubit, they can create a Schrodinger cat states up to 20 qubits. So there are several physical systems, which you have also heard in this conference, where people are trying to achieve quantum communication as well as quantum computation protocols. And the prominent ones are, of course, photons, ion trap, superconducting qubits, NMR, and also there are other like atomic or atoms in optical lattices. And yesterday you have heard about this nucleus spin in the diamond and so on. So in all these places, it is now possible to create a multi-site entanglement. That means it's a first step to build a quantum network. Now, let's go back to the literature that where it has already theoretically proposed that how to share entanglement over large distance. So the one of the prominent proposal is a quantum repeater, which you have also heard yesterday and in many other talks. So when you have, suppose I want to share entanglement between S and R, sender and receiver, and it's a large distance, then you actually divide this long distance into small segments. And these small segments or these nodals I denoted by N1, N2, and so on. And you perform measurement in all the nodes so that at final stage, S and R share some entangled state. Now you can see that if each of the each of this S and N1, each of these lines are connected by a singlet state, then of course, after performing Bell measurements at N1, N2, and so on, S and R also share a maximally entangled state. However, if in general in experiment these segments will no more be a maximally entangled state, but it will be a noisy state, then of course the final state S and R will not be a maximally entangled, or it will be also a noisy state. And the quantum repeater proposal says that okay, you start with many copies of rho in each segments, and then you perform entanglement distillation, and you create maximally entangled states between all these nodes. And finally, you perform measurements, say, for example, Bell measurements, so that S and R share a maximally entangled state. Now, we also, thought long back that can we remove this distillation step, because this distillation step that I have talked about actually requires, as you know, that you requires n copies of this row, and you require joint or global measurements in some of the, or collective measurements in all the distillation protocols. And this is hard to achieve experimentally. And the distillation procedure leads to a singlet state only when n is very large. So, it's actually quite the efficiency, as well as you require the many copies and so on. So there are a lot of difficulties to implement this distillation step in a real experiment. So we thought that can we remove this distillation step, and can we just ask the following question, that suppose each nodes share a noisy entangled state, then what is the critical noise that the initial state can sustain so that the final state remain an useful resource for quantum technologies? So S and R finally share some entangled state, which is still useful for doing some quantum information processing tasks. So this question was actually addressed some years back. I will come back to this question later. So before going into other details, let's discuss that what are the tools that I'm going to use to identify or to detect entanglement between shared state. So the certifying entanglement I will do by checking violation of Bell inequality. And this violation of Bell inequality I will calculate for bipartite scenario as well as multi-site scenario. So in bipartite scenario, I will use Clauser-Shimony-Holt inequality. As you know that these are the A1, A2 and B1, B2 are the two settings where the Alice and Bob perform measurements, and if B is greater than 2, then we conclude that the state violates Bell inequality. Similarly, I calculate multipartite Bell inequality, namely Marmin-Belinsky-Klitschko inequality. And also we know how to calculate it is also a two settings Bell inequality. And so in this sense, they too are kind of generalizations of CHSH to Marmin-Klitschko. And also I will calculate something called functional Bell inequality in a multipartite setting. So this functional Bell inequality was introduced by Marek Zukowski in 1993. And this Bell inequality is different than the one that I have described. So CHSH and Marmin-Belinsky-Klitschko inequality. In a sense that this inequality actually considered the settings, the measurement settings by Alice, Bob, Charlie, and so on, the continuous range of settings. I will explain in a minute what do I mean by that. So the basic principle in which the functional Bell inequality is written is as follows. In any real vector space, if you have two vectors, H and Q, then actually we know this is kind of Schwartz inequality, which tells us that the inner product between H and Q will be strictly less than norm of Q square, and that implies that H is not equal to Q. And now you can already guess probably that I take H as the quantum correlations something, and Q will be the local hidden variable model. So this is what exactly we have written. So this CQ is the correlations that you can think of for an n-party state. So rho n is an n-party state. These G1, G2, Gn are the observables at each site. And similarly, you can find out the correlations that you can obtain from the local hidden variable model. And you calculate the inner product. And suppose I can show that the inner product, modulus of the inner product is less equal to some number B. And at the same time, if I can show that this B is strictly less than norm of CQ squared, then it will imply that CQ is not equal to CLV, that means local hidden variable model. So that means the state actually violates the local hidden variable model or the local realistic model. That means we say that the rho n or the n-party state violates the functional Bell inequality. It was shown that if you have a GHZ state, for example, and if you can find an optimal measurement, and you can always show for n-party GHZ state that it violates Bell inequality. At the same time, later on, we have shown that for W states and other states, this functional Bell inequality, it violates functional Bell inequality. And actually, we have also shown some bound entangled states which also violates functional Bell inequality. And the important point is that the violation actually grows much faster than Marmin-Belinsky-Klitschko inequality with the number of parties. So this was already shown in a long back in a paper in 2003 by us, where we show that, for example, if you have a n-party bound entangled state, then the Marmin-Belinsky-Klitschko inequality violates it, the bound entangled state for n greater equal to 8. On the other hand, functional Bell inequality is violated for n greater equal to 6. Moreover, this functional Bell inequality has some importance or some consequence in an experiment, because for Bell test based on interferometric setups, one can show that this functional Bell inequality provides a greater robustness. because it scans the entire measurement settings. And in some sense, although the Marmin-Belinsky-Klitschko and other Bell inequality based on the finite number of settings, but in experiment, they actually scan the whole range. And so in that sense, the functional Bell inequality can be more useful. So these are the three Bell inequalities that I will use to certify a state to be entangled. Now here I should mention that most of the, in this talk, I will consider the noisy state that I have mentioned is a Warner state. Now, this Warner state is a 2-qubit state. As you know, it's a mixture of singlet and the identity operator or maximally mixed state. And this state has a lot of interesting physics, because we know that this state is separable when p is less equal to 1/3, and p greater than 1/3 it is entangled. On the other hand, we know that the state violates CHSH inequality when p is greater than 1/√2, that is 0.7071. So there is a range from 1/3 to 0.7071. There is the state is entangled, doesn't violate Bell inequality. But there is also a lot of twist here, because we know that till p equal to half, which is original Warner paper, where Warner has shown that this state, you can construct a local hidden variable model with projective measurements up to p equal to half. If you go to a POVM and so on, then there are a lot of results, which I'm not going to discuss. But the important point is that there are still a region where we still cannot construct a local hidden variable model, but also we don't know any Bell inequality which violates the state. There are a lot of work. As you can see, I have actually mentioned some of them. So still this state, although looks simple, but it has a lot of things which are still unknown, and people are working on it. Okay, so now I will talk about something which I have already mentioned. So this is super additivity in non-classicality, or activation in non-classicality. So first thing, before I talk about these activations, let us mention some of the results. So suppose all these nodes share a Warner states, and each node, this N1, N2 perform a Bell measurements, Bell basis measurement, so maximally entangled state measurement. Then one can show that after such n copies of the states, after performing Bell measurement, the final state looks like that. So you note that Warner state has the mixing probability p, and after such measurement, the final state has mixing probability p to the power n. So you can already see that these final state, that means the state shared by now S and R after the measurement, is violates Bell inequality when P is greater or equal to some number to the power 1/n. So we see that the state violates Bell inequality only when almost the state is pure. So it actually increases exponentially with n. So this is the first thing that I want to remark. On the other hand, we have shown actually a long back paper that suppose now I consider, okay, another point I want to mention, because here you must note that these final state can be obtained whatever measurement results that you get. So this is something different than the filtering operation, as I will discuss in this whole talk. That this method or the proposal that I'm going to show is something different than the other methods that are known. So now we consider a star network, we call it. This is where we again have n copies of the Warner states. And now one of the node is, say, these all nodes which are by Alice's side, they are together. So that in this scenario, you can perform Bell measurement, a higher party measurement like GHZ basis measurement. So for example, if you have 3 copies of the Warner state and you perform a measurement in the GHZ basis, then one can show that the final state looks like that. So it will be a mixture of GHZ, identity operator, and these projectors. And you can find when you have many copies, how the state looks like. And the important point is that the final state that shared between these far apart location violates Marmin-Klitschko inequality if P is greater than 0.7937. So this is the P which actually the initial state should start off the protocol. So in other words, suppose I find that my initial state, the mixing probability is 0.8. If I start with that, and if I have 3 copies of that, then the final tripartite state, this one, violates Bell inequality or violates Marmin-Belinsky-Klitschko inequality. Now, interestingly, we show that if we have 7 copies of such Warner state, and you perform a global measurements, actually in the GHZ basis of 7 party, then the output state violate functional Bell inequality when P is greater than this number. Now, what is the importance of this number? This number is lower, or it's smaller than the number 0.7071, which is 1 by square root of 2. So that means if I have 7 copies of Warner states with a P less than 7071, that means each of the Warner state doesn't violate Bell inequality or doesn't violate CHSH inequality, then after global measurement, the output 7-party state violates functional Bell inequality and or can show null locality or can show non-classicality. So this phenomena we called super additivity or activations in this paper. So this is, as I said, this is different than distillation protocol because here the joint operation is done by one of the nodes or one of the party, like Alice. Bob doesn't do any measurements. Bob only performs measurement to collect the statistics, for obtaining violation of Bell inequality. So this is after this global measurement. This is just to certify entanglement. And it is also different than filtration because in filtering, you actually require, you obtain these states probabilistically. Here also you obtain the state probabilistically, but every time, whatever measurement results you get, the outcome is always, so here, as I mentioned, that whatever is the outcome of the measurement results, always the output state is this state. So this is also different than filtering. So just to tell you that these super additivity questions or activation of quantum non-locality and hidden quantum locality by local filters, these are all, these questions were addressed in different times over the years. And this is an important question. This is one of the fundamental questions that people have addressed. And also now in quantum network, these questions actually kind of, so certifying entanglement, when we certify entanglement, at the same time, we can actually address these questions of activation. Okay, so I think so I have some time, right, Manav? I mean,
ITD, you have 5 minutes.
Oh, okay.
Yeah.
5, but I started at 15.
Yeah, so 30 minutes talk. And
oh, is it 30? I thought 40. Anyways.
and 10 minutes question answer.
Okay, okay. ठीक है, I will finish. So now I will talk about quantum network in 1D, 2D. So before I go to the quantum network, just to tell you that some observations. So suppose I have a GHZ state in tripartite scenario. Then this GHZ state actually, if you trace out the party C, then the two-party state, the resulting two-party state is separable because it's an equal mixture of 0, 0 and 1, 1. So it's actually useless. It's not only has not only is unentangled, but it also discord and other any quantum correlation measure is 0. On the other hand, if you perform measurement on C, then you may have something different, because suppose I perform measurement on C, but measurement I perform in the 0, 1 basis, then also the state is projected to either 0, 0 or 1, 1. So this is unentangled or useless state. On the other hand, if I perform a measurement in plus minus basis, then you can see that the state shared between A and B in both the cases will be maximally entangled. And so you can actually somehow sweep the entanglement after by choosing or by suitably performing measurement basis on C to AB. So this is this you can generalize to an arbitrary for arbitrary shared state. For example, if you have a tripartite state rho ABC, you can perform measurement on C, which actually leads to this ensemble pi rho I AB, and you can calculate entanglement between two parties of rho ABC, where you maximize over all the measurements on C, and this is the probability in which, sorry, this will be actually I or K, whatever. So this is the PI or PK at the measurement, the probability of obtaining the measurement outcome K, and correspondingly this rho 1, 2K is the measurement, the resulting state between A and B. And you calculate the suitable entanglement measures that you want to calculate. So this is possible to generalize for arbitrary number of parties, and you can, this is known as localizable entanglement or entanglement of assistance by Bennett and others, and so on. So we have done some recent work. If you are interested, you can look how it is behaving under noise. Now, suppose instead of this entanglement measure, I now consider the violation of Bell inequality. So I have an n party state. I choose suitable measurements on m parties and create this ensemble pi rho I n minus m. And now I calculate the localizable non-locality, which is actually this. So this is the pi is the probability of obtaining the outcomes. And this rho I n minus m is the, as you see, this is the output state, and you calculate the violation of Bell inequality. So this violation of Bell inequality, if you perform n minus 2 party performs measurement, then the output state will be 2 party. I calculate CHSH inequality, or I calculate if it is a multi-party, say M, then I calculate Marmin-Belinsky-Klitschko inequality or functional Bell inequality. So the building block that we have considered in our network is this, that I have already described. This is the star network. But here the difference between the previous work is the following, that here we suppose I start with n copies of this state, n copies say Warner state, then there is a global measurement which was performed by Alice or something, and then there will be a local measurement by some of the Bobs, so that the final states are either 2 party or 3 party or n party, whatever we want for our information processing task. So for example, in the bipartite case, so suppose you have a n number of Warner state you start with, and you perform a global measurement, and you perform also the local measurement in n minus 2 nodes. or these who are situated in distant locations, so local measurements and optimal local measurement, so that the final two states or the resulting two-party states, we want to see the violation. And we find that this is possible to actually calculate if we solve this expression. For example, if n equal to 3, so if we start with the 3 copies, then the criticality that we get is 0.869. And the criticality means that we have a initial state which we start with, and we know that this has this is unentangled from p less equal to 1/3. And as I mentioned, p greater than 1/√2 is CHSH violating region, and we get something pre-criticality, as you see, 0.869. So the states to the resulting two-party state, if we want a violation, then the initial state mixing probability should be more than 0.869. And we find that actually it increases, the peak criticality increases with increase of number of parties, and that somehow a bit bad news, because that means it actually, we have to have a more and more pure, close to pure entangled state if we really want to get a violations between two parties. Then we similarly calculate the, if we have an n party, and we calculate that if we perform measurements in m parties, and then what will be the n minus m party Marvin-Belinsky-Klitschko inequality, as well as functional Bell inequality. Now here is a good news, that you see that the criticality from which the initial state actually the noisy initial state that we want actually increases with or decreases with number of parties in case of multipartite Bell inequality. That means we can actually have a more and more noisy states we can start with, so that the final state violates Bell inequality. And here also you see, if you consider functional Bell inequality, then we find that the initial state can be non-CHSH violating, but the final state can violate functional Bell inequality. And again, we report superadditivity. But important point here to stress that more noisy states give functional Bell inequality violation, so it is robust against noise. And we also find superadditivity for functional Bell inequality. And I'm almost the end. So the similar building block can be used to show if we have a, if we want that multi-site or two-site entanglement can be spread over, say, this one-dimensional quantum network. And we again use Bell inequality to detect such entanglement. Here, these are the coordination. A is the coordination number. So red dot in the blue circle represent the coordination number. So in this graph, 4 is the coordination number. And number of nodes is actually this blue circle. So in this picture, there is also 4 nodes. And these blue circles, you perform the global measurements. And our proposal is that depending on the output state, number of parties output state that we require, we perform local measurements. Similarly, one-dimensional chain, we, in this kind of scenario, for arbitrary coordination number and the nodes, we can calculate that the output state violates Bell inequality if we can solve this inequality, which is possible to solve. Even for multipartite scenario, again, we find that to show multipartite non-locality, P criticality, that means the initial state noise, initial state P decreases with increase of coordination number. So it's robust against noise, and this robustness can be seen from this graph. And you see that we increase coordination number, and this green squares and red triangles actually decreases with the coordination number. That means we require less and less noisy states to obtain the violation of the resulting of the final state. And this is superadditivity can also be observed. I'm not repeating. Now, in two-dimensional quantum network, we have also studied. So, for example, triangular or square lattice. And we show that how to really obtain in terms of coordination number and the nodes, what will be the way to share, for example, entanglement between these red dots. But there is some interesting results. So we find the critical noise of the initial state to obtain so that the output state violates Bell inequality. But here probably we obtain an interesting results of superadditivity. We find that to obtain a Bell violating multipartite entangled state from non-CHSH violating bipartite states in a lattice, we require minimal coordination number to be 6. This we prove. And that means superadditivity or activations cannot be shown for two-dimensional square lattice. We require actually triangular lattice or something more, which has coordination number more than 6. So this is, I think, kind of these questions. We want to propose a two-dimension how to share entanglement and certify entanglement in a network. And this is a answer also. This gives us an answer of some fundamental question. Okay, so I come to the end. So as I said, we propose a method, which is a measurement-based method to share entanglement in a quantum network. And this entanglement can be spread, as I have shown, based on global and local measurement. And there is a possibility to certify that entanglement in experiments by using violation of Bell inequality. At the same time, this this answer can address the fundamental questions like superadditivity and activation. But we want to build, as I have already told you, that we want to build entangled quantum network because that is important in quantum communication network. These communications can be with or without security because in both the scenarios, we know that the entangled quantum network are useful. And probably we are aiming or we are heading towards quantum internet. So this is the current group of mine. So they are my Atul, Ganesh, Shoptoshi, Ribu, Srijan are my PhD student. Oyon, Pritham, Tona are doing projects with me. And Shiladit was postdoc now left. And this is the current group at HRI. So it's true that we have, I have told that there is a 15 PhD students, but there are 7 PhD new students are doing projects with the group. And so hopefully they will join. So the number will increase. So with this, I thank you all for attention.
Thank you, Aditi. It's a fantastic talk. Now we shall invite some questions from the audience. So if you have questions, please raise your hand. You can also write on the chat box in case you have some difficulties with your mic. So I see one hand raised. So this is Dr. Usha Devi. So Dr. Usha Devi, can you please switch on your mic and place the question? Yes.
I cannot hear Usha.
Dr. Usha Devi,
am I audible?
Yes.
Okay. Sorry.
Please go ahead.
So good to see you, Aditi, virtually. So the thing is, I wanted to ask you a question on Gison's paper in 1992, where he talked about hidden non-locality in a two-dimensional system itself, where if I use a POVM with 3 elements, then I may be able to show even in separable states, I will get a Bell non-locality, CHSH non-locality of 4. So when you are talking about different kinds of measurements in higher dimensions, would such problems be encountered is the question.
No, it's not. It's not because, you know, there, you are right. This is that paper actually, I mean, you know, as you know that if you are inside the quantum mechanics, Okay, so there is no possibility I mean,
No,
we
4
consider
you can't reach. Yeah. You cannot
so
reach the maximum of 4. Yes.
yeah. So what I am saying that when you inside the quantum mechanics, the inequality that I have considered is this CHSH functional or Marmin-Klitschko inequality. Then we know the upper bounds that we can reach. Okay. So for example, we know that in case of CHSH, we cannot go beyond 2√2. And similarly for Marmin-Belinsky and functional, we also know. So for example, functional, it is 2 by pi to the power n or something. Okay.
Yeah.
So,
Even
so
under
we
different
cannot go
measurement
beyond that,
schemes.
whatever way we go. Huh?
Okay.
Sorry?
Okay. Okay. Even under different measurement schemes that you employed, you don't encounter such
No,
issues. Is
because
what
I think we are always inside quantum mechanics, and so we cannot go beyond that.
Okay. Okay. Thank you.
Thank you, Dr. Usha Devi and Aditi as well. So is there any more question? I don't see any more hands raised. So if there is no more question, let us thank Professor Aditi Shende for this wonderful talk and the discussion. Thank you, Aditi, once again. And now I will request our next speaker, Dr. Min Jiang.
Hello?
Because, yes.
Yes, thank you.
Yes, now we can hear you. Maybe you can switch on your video also to check.
Yeah.
Yeah. So because of some technical difficulties, we had to shift his talk. So let me once again quickly introduce our second speaker. So Dr. Min Jiang actually received his BS degree in 2013 and PhD degree in 2019 in the University of Science and Technology, China. Now he is a postdoctoral fellow in the same university. His main interests are quantum precision measurements and nuclear magnetic resonance, in particular ultra high sensitive atomic magnetometer, ultra low field nuclear magnetic resonance, and tests of fundamental physics. So today he will be talking on 0 to ultra low field nuclear magnetic resonance and its applications. So Dr. Jiang, so please start your talk, and also it would be very much helpful if you kindly squeeze the talk a bit so that we keep up the time.
Okay, thank you. Thank you for introduction. And also, thank you. Okay, let me go. Okay. So is my slide visible now?
Yes, yes.
Okay, thank you very much. And also, I feel very sorry for the technical problem taking up your time. Yeah. So today, my talk, I will focus on 0 to ultra low field NMR and its applications. Yeah. So I will explain our recent work from 3 aspects. First is why we need ultra low field NMR, and the second, how to realize, and the third, what's the applications. So in history, NMR have been awarded 5 Nobel Prize, ranging from the physics, chemistry, and to the medicine. For example, NMR has very important applications in biological imaging, which is very useful for human medical diagnosis. So the detection of the NMR usually is based on Faraday induction pickup coils. So the sensitivity of such method is proportional to the biomagnetic field. So one of the NMR spectrometer and the development is trying to increase in the superconductor magnetic field. However, the corresponding price and the size of the superconductor magnet increased significantly. Moreover, the magnetic field inhomogeneity becomes worse and worse, thus required very complicated technical for assuming the magnetic field. So currently, the state-of-the-art spectral resolution is limited to about 100 millihertz. So in addition to the price and the size problem, traditional NMR remains challenging in several researches. As shown this slide, for example, traditional MRI is unavailable to human with pacemakers, because if the human with pacemaker, when it moves in a magnet, it will generate an inductive current. So it's very dangerous for the human. And for other researchers also have stable problem. For example, for the battery, it will generate electromagnetic interference for the NMR spectrometer. So people begin to consider how to solve the above challenge problem. One of the promising way is to remove the large magnetic fields. Professor Eriks and Professor Dimitri Budka are the pioneers of the ultra-low field NMR. Such new NMR protocol has have several advantages. At first, it doesn't require a superconducting magnet, so it could be very cheap and also have a high portability and also very safety. In particular, it doesn't require a superconducting magnet, so it have a very high magnetic field homogeneities. Thus, it can realize millihertz resolution NMR spectrometer. I will show later about the detailed results. So in the following, I will try to introduce I try to explain how to realize the low field NMR. So as explained before, usually in the traditional NMR is using peak inductive coils to detect NMR. However, this method is failed to detect low frequency NMR signals. We can see from this profile. So the sensitivity becomes worse in the low frequency. So it is highly desirable to develop new sensors for ultra-low field NMR. So currently, there are 4 main magnetometers in the world. For example, squeeze atomic magnetometer, NV standard, and also proton magnetometers. Compared with these 2 squid and NV standards, atomic magnetometers is currently the most sensitive magnetometers in the world. For example, the state-of-the-art atomic magnetometer could reach sub-femtotesla sensitivity. Moreover, atomic magnetometer doesn't require the low temperature system compared to the squid, so it could be make it very small. It also can combine with nanotechnology, so the magnetometer could be small and highly sensitive. So let me introduce about the principle of the atomic magnetometer. So usually we use the glass cell contained a droplet of alkali atoms and is heated to produce very high pressure alkali vapor. And then we can apply the circular polarized pump laser through the atoms and then align nearly all of the electron spins along the pump laser. And then we can apply the small magnetic field. This field usually is what we want to measure. Then because of the Zeeman interaction, it will reorient the electron spins. So as a result, the index of the refraction of the atomic gas will change. So this change in optical properties, it can be measured. It can be measured by detecting a Faraday rotation of linear probability. It means if we send a linear probe laser pass through this web cell, it will have a Faraday rotation. And also, the measured optical rotation is proportional to the small magnetic field, so the output signal could be acted as the magnetic field sensor. So let me give you an example. So in our experiment, we use a cubic web cell. The size is about 1 centimeter. And then we put some rubidium-187 atoms inside, and then we heat it. Then we put the NMR sample in a standard 5mm tube, and then we put the tube close to the web cell. The distance between them is about 3mm. Then the NMR samples can seem as like a small magnetic field moment, which can generalize a weak magnetic field on the web cell. So we can use this very sensitive atomic magnetometer to detect the magnetic field generated by the NMR samples. And then here is our ultra-low field NMR spectrometer. This is this is the Hebeck magnet. It's a 2 Tesla. We didn't require its magnetic field homogeneity. We just normal, just the 2 Tesla. And then we put a sample inside for pre-polarization for adhere about half a minute, and then transfer from the high field region to the zero field region. The zero field region is produced by a 5-layer magnetic shield. Inside the residual magnetic field is below, usually is below 1 nanotesla. We also calibrate the sensitivity, magnetic field sensitivity of the magnetometer. We can see this figure is about 10 femtotesla per root hertz in the low frequency. So in this region is very sensitive than the traditional inductive coils. So this figure is one example low frequency, low field NMR signal. The sample is the formic acid. The sample of which the carbon is labeled by carbon 13. And what we measured is the J coupling between carbon and the proton spins. It has a typical oscillation frequency about 222 hertz. And then we can also see from the free decay signal, we can see the spin realization time is about 10 seconds. It's very, very long compared to the electron spins. Yeah. So we also use this setup to measure other samples, for example, the methanol and acetonitrile and so on. Yeah. So to further improve the signal to noise ratio of NMR signals, we first applied the atomic gravimeter to detect NMR gradient signal. So this is our setup, gravimeter setup. It has 2 channels, the channel 1 and channel 2. These figures use the signals from the single channel raise the very significant noise. In contrast, we can calculate the difference between them. We can see very clearly signal oscillation signal. The signal to noise ratio is increased at least 10 times. Yeah. Okay, so this is our recent advances on building NMR spectrometers. We can see the sensitivity from 2013 and to recently is increased from 18 femtotesla per root hertz to 7 femtotesla per root hertz. And recently we are working hard to improve the sensitivity to 1 femtotesla level. So if in the near future we can reach 1 femtotesla level, it is convenient to measure samples with natural abundance. This is very important for the chemical size and material size. Yeah, because usually in a sample, for example, the carbon 13, the natural abundance is only 1%. So if we can reach 1 femtotesla, we can measure the natural abundance samples just single shot measurement. So recently, we are also invited to write a review paper on zero and ultra-low field NMR, usually called the ZUF NMR, and its applications, including from we systematically summarize the ZUF NMR and its 5 main applications. In the following, I will introduce our work about the material size and the test of fundamental physicals. So first, about the material size. In general, there are 2 types of interaction between nuclear spins. First is the Zeeman interaction. The second is the local interaction. So the local interaction usually include the 3 couplings: dipole-dipole, J coupling, and quadrupole coupling. But for the liquid, dipole-dipole and the quadrupole coupling are average to 0. So usually for the liquid, there is only J coupling. Now let's compare the Hamiltonian in high field case and the ultra-low field case. So we can see in high field NMR, because the magnetic field is so large, so the Zeeman interaction is dominant. In contrast, zero and two absolute field NMR, the local interaction, for example, for the liquid, J carbon is the dominant. So this means we can imagine a pure local interaction without any influence from Zeeman interaction, just in zero and absolute field NMR. Here are some examples. We can simply measure the J coupling between carbon and the proton spins. For example, the first sample is the formic acid. The carbon and carbon to the proton in zero field raise only one peak at the exactly J coupling. So from this peak, we can simply achieve the J coupling strength. And for other sample, we can also simply achieve that. Here we note one problem, raise the ambiguity to distinguish the different function groups. For example, for the XA and XA2, they both show a single peak. So usually we cannot distinguish which function groups. So to solve the above problem, we can simply apply the very weak magnetic field on the samples. For example, just 100 nanotesla. So we can see in the sample, we can see the Zeeman splitting are different for different samples. The formic acid split to 2 peaks, but for XA2, it's split to 4 peaks. So based on the splitting number, we can simply distinguish the different function groups. Yes. And also we find the spectral amplitude as symmetric. For example, for the left peak amplitude, it's smaller than right peaks. This phenomenon is very general in a wide range of samples. Let me give some details. This is formic acid. The left peak is smaller than the right peak amplitude. But however, according to the textbook theory, these two peaks should have same amplitude. However, compared to the experiment result, which is the result is quite different. So actually, this asymmetric phenomenon have been observed since low field NMR was first time realized in 2011. Although many groups are trying to explain the asymmetric phenomenon, but it is unexplained. So until recently, we find raised an interferencing factor in atomic magnetometer. We can see from this figure, then atomic magnetometer could be simultaneously sensitive to the magnetic field along X and Y axis. And also we note they have a different phase response. So different NMR transition peak, it can generalize the magnetic field along X and Y, and then they will interference each other inside the atomic magnetometer. So it will, and also different transition will have a different interference strengths. So they will cause a asymmetric amplitude. Yeah. So if you have an interest in, you can also check this paper. Yeah. So about the above work, our paper was selected as a front cover and claim that interesting new interference phenomena are anticipated for a wide range of systems. Okay, now I will introduce a bit about dark matter stages using the zero to absolute field NMR. Yeah. So in Science Journal, it will point out 125 big questions. The top one is, what's the universe made of? So based on many astronomy study, for example, the gravity lensing effect, they are dark matter comprising of our universe 18% material. However, what kind of particle made of the dark matter is still unknown. So as we know, the standard physics models is one of the most successful model to understand our universe. This is the elementary particles, and this is the 4 kinds of basic element interactions. However, the standard physical model cannot explain the dark matter. So it should develop the theory beyond the standard physics models. Axial and axial-like particles are such kind of particles beyond the standard model. So they are well-motivated candidates of dark matter. There are several in the world currently. There are several large startups to try to explore it. For example, the LHC, Castor, and the Pandex. Yeah. Even though a lot of money and the people trying to explore it, but axial have still not found yet. So recently, there is a science review paper point out laboratory scale experiment devices also can be used to search for new physics beyond the standard model. So in particular, many precision techniques based on atomic and molecular physics are very sensitive to the magnetic field and electric field. I will show later. The dark matter can generalize and effect magnetic field on nuclear spins and shift the energy levels of the spins. Then we can use a spin sensor to hunt for axial-like dark matters. So Professor Dimitri Burka several years ago proposed that NMR may be a good setup to search for axial dark matters. Here we can see this Hamiltonian. The Hamiltonian is described in the axial and the nuclear coupling Hamiltonian. The dark matter can generalize an effective magnetic field.
Dr. Min Jiang, we cannot hear you. Dr. Min Jiang, we lost your voice. Can you hear us? We cannot hear you. But we cannot hear you. Can you check your mic in case? No, we cannot hear you. Dr. Ming Jiang, we still cannot hear you. So your slides are still on share mode. Do you lost your voice?
Now,
The voice is breaking. I just hear something, but can you please try once again? Can you please say something if I can hear? Yeah, the voice is breaking.
Yeah. Okay.
Okay. Yeah,
Okay.
now it's better.
Yeah, thank you. Sorry.
No
So
problem.
yeah.
So you have to share the slide.
Oh yeah.
Yeah. So it will be helpful if you kindly go towards the conclusion.
Yeah. Okay, so I try to share my slide. Yeah. Yeah, my slide is visible.
Not yet.
Not yet.
Not yet means it's not loaded yet.
Yeah. How about now?
Not yet.
Not yet.
It's not loaded. It just shows black screen.
Yeah, maybe.
Now I can see.
Okay.
Now we can see.
Okay.
Yeah.
Yeah.
Please go ahead.
Yeah, let's move it. Yeah. So okay. So okay. So the dark matter could be generalized effect magnetic field. So we try to make build more sensitive detector, so it can be imagine a smaller coupling, and the lower frequency could imagine a lighter actual like dark matter fields. Yeah. So this is our purpose. So we can, based on this principle, we trying to image, we could do angular measurement of dark matters. Let me explain how we prevent impairment stage. In general, the magnetic field sensitivity is described by these equations. So in which the spin position and the T2 are very important. So so here we choose a noble gas because it could have very long T2. It could reach 10 seconds, and the spin position could be doing a hyperposition. Yeah. So let's compare the different noble gas. So Hero 3, because of the natural abundance is very low, so we choose the Zeno 129. It have even though the T2 is shorter than the Hero 3, but the natural abundance is high. Yeah. So this is our setup. To polarize the Zeno gas, we mix the Zeno gas and with the rubidium 187 gas in the same Weber cell, and then the rubidium could be optical pumped, and then it can transfer to the Zeno gas. Yeah. So here is our impairment result. We can see from this free decay signal, we can see we can achieve the SNR is above 5,000. So the spin position could be estimated to about 10%, which is 4 orders of magnitude larger than the thermal equivalent in 10 Tesla. And also we could see from the free decay on the Leibniz, we can see the T2 is about 20 seconds. However, the 20 seconds is still not enough for our research. So we're still trying to think about how to further improve the coherence time. So in this part, I will try to explain how we solve the coherence time. So here we are inspired by Maser technical. Maser have gotten Nobel Prize in 1964. The population inverted system injected into a cavity. When the throttle is satisfied, a continuous oscillation can be built. So actually, this is the model of an atomic clock. The cavity is.
Excuse me, Dr. Minjiang. It would be really helpful if you kindly go towards the conclusion soon.
Sorry? It
would be really helpful if you kindly go towards the conclusion soon.
Yeah. Sorry. Yeah, I will quickly.
Thank you. Thank you.
Sorry. So this is our setup. Yeah, and I show you some results. So this is our Maser at on 10 Hz. Yeah, and also we apply the AC magnetic field. We see the peak. We are splitting to different. Yeah. So we try to actually the Maser is different. So we call the Maser is called Brookwood Maser. It's quite different from the textbook. Yeah. And then this is more complicated examples. We can see the Maser have more than 100 transition lines. Yeah. So this is we also use this Maser to realize the magnetometer. It could be very sensitive to the low frequency. Yeah. Okay, so this is our setup for hunting for the axial-like dark matters. Yeah, currently is working well and trying to search for the dark matter. And okay. So In the future, we join out this GNOME system to build a master network, and this in end, we thank you for your attention.
Thank you, Dr. Min Jiang. So we have time for one question. So if you have a question, please raise your hand, or you can also write on the chat box, Zoom chat box. Is there a question? Okay. So okay, it seems there is no question at this moment. I think the audience still has to digest quite a lot of information and interesting topic you have discussed. But in any case, if there is some question, I think you can directly write to Dr. Min Jiang, and I'm sure he will entertain and answer these questions. Okay, so with this, I will go towards the end of this session. So once again, before I go, let me thank Dr. Min Jiang for this interesting talk. And now we are actually at the end of our first session of the day. And with this, I would like to thank both of our speakers, Dr. Min Jiang and Professor Aditi Shende. And with this, I would hand over the session or the program to Dr. Sandeep Goel. Thank you.
Thank you, Manav, and thanks to all the speaker of this session. It was a wonderful session. Now we have a poster session, and like yesterday, all the information about the posters is available on the program tab on our QFTA website, the same place where you find all the details about all the talks. So you can just click on the poster session button, and you will be taken to all the PDFs of the poster. And when you click the PDF, you will find the detail of the speaker and the chat room, the video chat room at the bottom of that PDF. So please move forward to see the posters. We have some very exciting work in those posters. Thank you.